We've been joined by Alfred Boulanger from Columbia University, I believe, and he'll be our last presenter of this panel.
I don't have a name plate here, but I saw it printed. But there's my name. I'm with the Center for Computational Learning Systems at Columbia University and the World Team Now nonprofit. And those are my contacts. And what I want to talk about is smart grid thinking, a term called innervation and infrastructure threats. Some thinking here is the keys to a resilient smart grid. One of them has been a new way of doing SCADA. There's disruptive technology coming in. What we see is self-locating, self-organizing, self-identifying, and these sensors that are being placed, in this developing field of the Internet of Stuff, is they produce, the data they produce can be self-storing. The other point is, in order to control, one needs to model. So if you have a resilient power grid, its objective is to try to deliver power reliably as possible. And one needs to model. And, so traditional models are like power flow models. But we also want to model the reliability to the grid, component failures, statistical approaches to doing that. In the control aspect, when you think of a grid and trying to get it to achieve its objective, fundamentally it's a multi-stage stochastic optimization problem where you have decisions in the futures and you want to create what they call policies, and they're like policies that we know, but algorithmic policies that will give you optimum choices under uncertainty into the future. And the algorithms that we develop are called approximate dynamic programming algorithms. And I'll go through 5 examples of that I have listed here in some slides coming up. Grid and local storage, to increase elasticity of the grid is very important. There's a key component to making the power grid more resilient. So electrons disappear if you turn it off. Storage is a key for providing the notion of elasticity. The grid is very brittle, if you will, without that kind of elasticity. And then finally, policy changes and awareness are important. Highlight that, a project that I was involved in upstate New York. Somebody wanted to put in a solar panel on their house, and they wanted to net meter it. They go to the town, and they say, I want to put in a net meter. What's a net meter? Nobody knew about what those were or what the town's procedure for allowing it to be installed was. So awareness certainly is important in placing the new components to the smart grid. The innervation is basically, the concept is innervate comes from to innerve a whole organism, being a grid. It's a combination of centralized and local control. The nervous system has parts of it that is more autonomous than the central brain, and then there's the central brain. So architectures, hierarchical architectures like this, where decision-making can be done at a low level as well as a high level, is probably a key for the robustness of the networks that we build. This Internet of Stuff that we're talking about, before the Internet, there was SCADA systems. SCADA systems were developed, I guess back in the 40s to control the last mile for companies that had last mile assets like water companies, oil and gas companies, and power companies. And they used the technology of the day, which was twisted wire and leased lines to be able to sense their distributed assets. Nowadays, we can rewrite this, and with now it's probably a little old, but I did this slide in 2000, early 2000. You know, that this disruptive technology is happening. So the TP is actually occurring as we talk. Another point is that on this with this innervation is that the innervation has to go across systems. So this is from a slide, a report by Perenboom in 2001. And I think we've seen all these dependencies. Every time there's the 9/11 and Sandy, the dependencies become exposed. You know, in order to pump gas, you need electricity, and you can't deliver your fuel to the places. So gas lines and shortages occur because of these dependencies. Our group has been doing some smart grid work in collaboration with Con Ed, and I'll go through some of these examples of using approximate dynamic programming. ThreatSim is a learning simulation system that I thought with Roger Anderson and my group back or after 9/11. And the idea was to use a combination of learning, machine learning, and simulation to learn how to deal with threats. So you can think about desktop exercises and basically building a computer version of that where we use models and a learning system on top of models to learn optimal policies based on what you can simulate. A caveat in all this simulation I should mention is that nobody, I don't think, could really say they can deal with the fat tail problem or the black swan problem. This is a huge problem in building resiliency. You know, a fat tail, the distribution is fatter. We suffer from the limitations of being able to simulate reality, especially in this area where you have fat tails. But an LSOC is a system we developed for the Smart Grid project with Con Ed. We made distributed resource control precise. So load shedding is pretty wide sweeping when Con Ed decides to do shedding. How can we make this more precise? And using these approximate dynamic programming algorithms to do that. Dynamic treatment involves the reliability side. If the system, we use statistics, we build statistical models and machine learning models of failures of components, and we borrow the concept from dynamic treatment regimes in medicine where you can optimize your repair strategies, your inspection strategies for the patient. Each patient, each feeder, for instance, is treated as individual, and we build a statistical model for them to make optimal decisions on their repair. And on the other side of the transformer is also important. We have several projects we've done here, one with GE, FedEx, and ourselves on optimization of electric delivery truck charging. And we won an Equal Imagination Award for the work. And also, we're currently involved in intelligent operation of skyscrapers. ThreatSim makes use of models and a learning harness. I call it a learning harness that you can simulate both the transmission and distribution grids and introduce scenarios to that so it can learn policies, restoration policies based on simulations. This is a poster that was put together for the Smart Grid program, and we were involved in a load and source controller and this dynamic treatment as part of this program. Here's a slide describing the FedEx project that we had, and we were building the forecasting models that predicted the charging load and the building load for this project. In the Smart Building Systems project, what we're doing is we're using machine learning to forecast building performance, building behavior for the next day, so we can make optimal choices about turning on and turning off systems in the building. Storage is a key in new battery technologies coming along, like the EOS zinc air battery, which has much better properties than a lot of current batteries like sodium sulfur or lithium ion. So there's going to be some changes in the batteries landscape that will help enable storage. And thermal storage, which can displace electrical storage in buildings, for instance, helps with this as well. Policy and awareness is important. I think we all know. You know, contrarian policies don't help bring new technology forward, and lack of knowledge that it even exists hinders adoption. And there's roles of organization to change policy, and the nonprofit I'm involved in is involved in this awareness and policy area. Finally, leave you with two quotes, very, I think, appropriate for what we're talking about. The future ain't what it used to be. And finally, no problem can be solved at the same level of consciousness that created it. So with that, that's it.
Thank you very much.